The paper today is Kwai-VL-2.0-30B-A3B, an open source MOE multimodal foundation model.
Right to it.
Yeah, no fluff. Welcome to AI Paper Slop, where we break down the latest AI and tech papers for the engineers and researchers who are, actually building this stuff. Here are the core insights you need right now.
Let's hear them.
Kwai-VL 2.0 is a 30 billion parameter mixture of experts foundation model, but during inference, it only activates 3 billion parameters.
Which is incredibly lightweight.
Exactly. And it achieves a completely lossless 256K context window, which means it natively handles hour-long videos. It pulls this off by being the first model to successfully adapt DeepSeek Sparse Attention into a grouped query attention multimodal architecture.
Right, which is huge.
Yeah, and more importantly, it solves two massive bottlenecks in agentic AI. First, it just crushes the infrastructural nightmare of the KV cache explosion.
Oh, absolutely.
And second, it solves the algorithmic multimodal alignment dilemma. That problem where a model suddenly forgets how to do basic math just because you taught it how to navigate a graphical user interface.
Mm-hmm. Yeah, the catastrophic forgetting issue.
Exactly. And they fix that using a novel cross-modal multi-teacher on-policy distillation method. So a lot to unpack there.
It really is a masterclass in decoupling extreme context capabilities from, extreme computational cost.
Yeah.
I mean, for any of you currently designing multimodal architectures, the blueprint they've laid out here is incredibly practical.
Right.
It shows how to scale capabilities without completely melting your GPU clusters.
Let's start with that architectural bottleneck, actually, because beating the KV cache explosion is essentially the holy grail of long context video right now.
Yeah, it's the biggest wall we hit.
Right. We all know the math standard dense attention mechanisms scale quadratically. If you try to feed an hour-long video into a dense model, the memory required to store the key value cache just blows up.
It's just mathematically impossible at a certain scale.
It hits a computational brick wall. So how does Kwai-VL 2.0 actually bypass this quadratic scaling?
Well, they do it by integrating DeepSeek Sparse Attention, or DSA, directly into their grouped query attention backbone.
Okay, so bringing DSA into GQA.
Right. Normally, in a standard dense attention setup, every single query token has to attend to every single previous key value pair.
Which is fine for a short prompt, but...
But if you have, say, 256,000 tokens, that matrix multiplication is astronomically expensive.
Yeah.
So instead, Kwai-VL 2.0 uses what they call an MQA-style lightning indexer.
A lightning indexer, what does that actually do?
It generates global index scores for all the tokens, but it enforces a hard cutoff. It only keeps the top 2048 tokens for the actual attention calculation.
Wait, just 2048 out of the whole 256K?
Exactly. By forcing the attention mechanism to only aggregate over this small, fixed, sparse set, they fundamentally change the math.
Oh, wow.
Yeah, they drop the attention complexity from quadratic to essentially linear.
That is a massive optimization. And it's not just the attention mechanism they overhauled, right? They totally changed how the visual encoder maps the video frames to begin with.
Yeah, they had to.
Because historically, if you had high-resolution images or varying aspect ratios from different video sources, the standard practice was to force them into fixed-resolution crops or tiles.
Which is terrible.
It really is, because it just destroys the global structure of the image. But Kai-VL uses a native resolution vision encoder based on SIGLIP 400 Mir.
Which is then paired with adaptive position encoding and 2D ROPI or rotary position embedding.
Right, 2D ROPI. Let's unpack that for a second.
Sure. To understand why 2D ROPI matters, just think about standard 1D position embeddings. They just count tokens in a straight line, right?
Like reading a sentence, 1, 2, 3.
Exactly, which is fine for text. But 2D ROPI independently encodes the X and Y coordinates of the image patches. It maps the spatial relationships mathematically.
So it actually understands the geometry.
Yes. So whether the model is looking at a massive ultra-wide cinematic video frame or like a really tall, skinny screenshot of a mobile receipt.
The mathematical representation of space remains perfectly intact.
Exactly. The model understands the layout natively without needing to distort or crop the source material.
I just love the elegance of their unified visual encoding strategy here. I mean, instead of engineering some ridiculously heavy, specialized video encoder that tries to model the concept of time at the pixel level.
Right, which never really works well anyway.
Exactly. Instead of doing that, they lean into the language model's existing strengths. They treat the sampled video frames simply as independent, high-resolution images.
Just handing the model a stack of photos.
Yeah, like handing it a stack of high-res photos with Post-it notes on them. They just prepend a natural language timestamp to each frame. The text acts as an absolute temporal anchor.
It essentially offloads the burden of understanding time from the vision encoder to the LLM.
Which is so smart.
It is, because the LLM already understands what minute 12 second 4 means in relation to minute 14. It makes cross-frame reasoning so much easier to optimize because all that temporal logic is happening in the model's native language space.
Okay, so I follow the logic on the visual encoding, but I'm getting stuck on the map of the sparse attention again.
Oh, the 2048 token limit.
Yeah. If we are only keeping a sparse set of top 2048 tokens using that lightning indexer, how does the model not just hallucinate over the gaps?
That's a very valid question.
I mean, if I feed it a 2-hour video and the critical clue say, a license plate on a passing car is only visible for 3 frames, keeping only 2048 tokens seems dangerously sparse. Doesn't the indexer just skip over that microevidence?
That vulnerability is exactly why you can't just train a sparse indexer from scratch randomly. It would absolutely miss the license plate.
So how do they fix it?
They implemented a very specific 2-stage training strategy to prevent exactly what you just described. In the first stage, they run a dense warm-up phase.
Dense warm-up, meaning it looks at everything.
Everything. The main model operates using standard dense grouped query attention. While it's doing that, the sparse indexer is trained alongside it. But, and this is key, it isn't controlling the routing yet.
Oh, so it's just watching.
Basically. They compute a KL divergence loss between the sparse indexer's predictions and the dense model's actual attention distribution.
So the KL divergence loss is mathematically forcing the sparse indexer's probability distribution to match the dense model's distribution.
Exactly. It's learning the exact attention map of the dense model. They feed it about 2 billion multimodal tokens in this warm-up phase alone.
Wow, just to learn where to look.
Yeah. The sparse indexer's only job is to practice finding the exact needles in the haystack that the dense model would have looked at anyway.
Ah, I get it. The KL divergence penalty ensures that if the dense model found that split-second license plate, the sparse indexer learns the pattern required to flag it, too.
Right. And only after the indexer proves it can perfectly mimic that dense intuition do they unfreeze the parameters and switch to full sparse adaptation.
That makes perfect sense. It preserves the pinpoint accuracy of the dense attention, but drops the inference overhead permanently once the training wheels come off.
Exactly.
But, building the architecture to hold a 256K context window without crashing is really only half the battle. You still have to figure out how to train the model to actually use that space without destroying its core capabilities.
Right, which brings us to their pre-training curriculum.
Yeah, let's get into that. It's broken into 4 distinct stages, right?
Yeah, from stage 0 to stage 3. Stage 0 sets the entire foundation, and it is purely an exercise in risk mitigation. They call it projector initialization.
Risk mitigation? How so?
Well, at this point, the vision transformer and the large language model are both completely frozen.
Frozen, so they aren't learning anything new yet.
Nothing. The only thing they are training is the MLP projector, which acts as the bridge between the two modalities. They train this bridge on about 4 billion tokens of image-text data.
Ah, okay. So by freezing the LLM, they prevent that massive language engine from receiving catastrophic noisy gradients while the visual pipeline is still figuring out how to format its outputs.
Exactly. You don't want to shock the LLM with dense visual signals before the projector knows how to translate them cleanly.
That isolation protects the core language reasoning.
It does. And once that projector is initialized, they move into stages 1 and 2, where they sequentially ramp up both the context length and the task complexity.
Right, I saw that. Stage 1 expands to a 32K context for general alignment, and then Stage 2 pushes it to 64K for multitask capability injection.
And the order of operations in Stage 2 is really critical.
Yeah, they flood the model with high-quality optical character recognition data first, right? OCR, then STEM problem solving, and finally GUI navigation, like interacting with web browsers or desktop environments.
And the causal relationship between those data sets is highly intentional.
Meaning one builds on the other.
Exactly. You can't expect a model to reliably navigate a complex user interface if its foundational OCR isn't rock solid. It has to be able to read the pixelated text on a button before it can learn the logic of when to click it.
That makes total sense. They are layering structural, verifiable tasks so the model understands absolute ground truth logic.
Right. Which leads perfectly into Stage 3, the long context extension, which finally unlocks the full 256K window.
But what caught my eye in Stage 3 wasn't just the sheer size of the context, it was their data mixing strategy.
The 1-to-1 ratio.
Yeah. When training on these massive contexts, they mix the long context samples the hour-long videos, and massive multi-page documents with short context samples at a strict 1-to-1 ratio.
And that 1-to-1 ratio solves a really well-documented degradation issue in the field.
Really? What happens if you don't do that?
Well, many foundation models, when they're fine-tuned to handle ultra-long context, start getting sloppy on short, punchy, zero-shot queries.
Oh, interesting. So they lose their edge on the easy stuff.
Exactly. Their attention mechanism gets lazy because it's used to hunting across 100,000 tokens for context. By forcing the model to constantly alternate between a massive agentic trajectory and a simple, direct question, it maintains its short context precision.
So they've locked in the context window, and they've kept the short context sharpness. But scaling up to complex agentic capabilities introduces a completely different threat.
The algorithmic dilemma.
Right. This is the core algorithmic dilemma addressed in the paper. Because the moment you start teaching a multimodal model how to use tools, write code, or execute multi-step GUI navigation, you almost always trigger catastrophic forgetting.
The model becomes a great software engineer, but suddenly forgets how to do basic algebra or linguistic reasoning.
Exactly. The industry calls this the multimodal alignment dilemma.
And it happens because if you try to perform end-to-end co-optimization of wildly different domains, like, say, creative writing and strict Python coding, the gradients clash, it creates massive instability during training.
So how does KaiVL fix this?
To fix this, the team introduces a synthetic data reinforcement learning framework. They start by procedurally generating difference recognition tasks.
Difference recognition, like spot the difference.
Yeah, exactly like that. For instance, they will systematically alter a geometric shape or a complex chemical formula and ask the model to spot the exact edits.
And crucially, they verify the model's performance on this using strict rule-based verification. Because the data is procedurally generated, the exact mathematical edits are already known.
Which is infinitely better than relying on a learned reward model for this specific step.
Oh, for sure. Learned reward models are notorious for hallucinating or just being easily gamed by the student model.
Right. When the edits are grounded in procedural generation, the reward signal is absolute. It's undeniable ground truth. They then optimize this using group sequence policy optimization, or GSPO, heavily paired with context ERL.
Let's unpack context ERL because that feels like a critical piece of the puzzle here. How does it actually change the policy optimization?
Context ERL evaluates the trajectory of the logic, not just the final output.
Showing your work.
Exactly. In standard RL, if a model guesses the right answer, say C, on a multiple choice math problem, it gets rewarded, even if it used completely flawed, hallucinated steps to arrive at C.
Which reinforces bad reasoning.
Right. Context RL actively penalizes those false positives. It ensures the model is rewarded only when the reasoning steps logically support the final answer.
Which drastically reduces hallucinatory shortcuts in complex agentic tasks.
Exactly.
That secures the logical reasoning, sure, but it doesn't solve the domain clashing we talked about. This is where we have to talk about their standout algorithmic fix. Cross-Modal multi-teacher on-policy distillation, or MOPD.
Yes, MOPD is brilliant.
Instead of trying to blend everything into one messy reward model, they maintain 13 separate, highly specialized RL-trained domain teachers.
Right. There is a teacher specifically for math, one strictly for coding, one for video comprehension, OCR, tool use, and so on.
And when the main student model is generating a response during training, the routing system sends that specific sample to the most relevant teacher to get incredibly dense token-level feedback.
Correct.
I get the concept, but mechanically, how do 13 different expert teachers not just create absolute chaos?
What do you mean?
Well, think about it. A coding teacher's preferred token distribution is going to look completely different from a creative writing teacher's. If you have all these distinct teachers correcting the model at the same time, how does the student not just output a chaotic style-clashing mess?
That is the exact problem MOPD solves. They use a dynamic routing mechanism combined with something called the top K overlap set. It's almost like pair programming between the teacher and the student.
Okay, pair programming. How so?
Imagine the student model is about to predict the next token, and its internal logic suggests 3 possible tokens that seem good. The teacher model also analyzes the context and suggests its own top tokens.
Okay, so they both have a list.
Right. But the teacher doesn't just delete the student's work and force its own arbitrary perfect token into the sequence. Doing that across 13 different teachers would totally shatter the model's unified style.
So what does it do?
The system looks at the top K overlap. It isolates only the tokens that both the teacher and the student agree are mathematically plausible.
So it only optimizes within their shared consensus.
Yes. The teacher gently reweights the probabilities within that overlapping subset of tokens. It nudges the student toward the best possible answer that the student was already considering anyway.
That is so smart. Supervision is strictly applied to the local distribution region that both models find acceptable.
Exactly. And to make sure the math aligns perfectly during all this, they use segmented prompt response retokenization, or SPRR.
SPR.
Because if the teacher and the student process text slightly differently at the tokenizer level, the feedback gets corrupted. SPR aligns the teacher's log probabilities so they map one-to-one with the student's tokens.
And that precise alignment is what allows KaiVL 2.0 to essentially absorb the deep, localized expertise of 13 vastly different domains.
Yes, without the gradient updates destroying the model's underlying stylistic coherence. It integrates the knowledge back into the 3 billion active parameter MOE backbone safely.
All of this algorithmic elegance, the MOPD, the top K overlap, the context RL, it's brilliant. But if it bottlenecks at the hardware level, if it starves the GPUs during training, it's basically useless in production.
Oh, 100%. The infrastructure engineering in this paper is just as important as the math.
So how did they stop the video decoding process from starving the GPUs? Because video is heavy.
Video decoding is notoriously heavy on CPU and I/O. If you process it sequentially, your GPUs are just sitting there idling while the CPU unpacks frames.
Which is a massive waste of money.
Huge waste. So they decoupled the entire video decoding process from the training pipeline using an asynchronous service they call Extra I/O. It handles the heavy lifting in the background, so the data stream to the GPUs literally never pauses.
And they went a step further with VET-LM heterogeneous parallelism.
Yes, this is a great optimization.
Because in a standard pipeline parallelism setup, the vision transformer and the language model layers are locked together across the GPUs. But a vision transformer processing thousands of high-resolution patches operates at a completely different data granularity than the language model.
Which creates massive bubbles in the pipeline.
Right.
Those bubbles are just periods where GPUs sit doing absolutely nothing while waiting for the other component to finish.
Sure.
Heterogeneous parallelism untethers them.
So they aren't locked anymore.
No. They split the sharding strategies, so the VIT and the LM are mapped to the hardware independently based on their specific compute loads. It keeps utilization exceptionally high.
That handles the training side perfectly. But what about inference? I mean, running a 30 billion parameter model with a 256K context sounds like a fast track to bankrupting a startup.
It does, but this is where those earlier DeepSeek Sparse Attention optimizations truly shine.
Oh, right, the linear scaling.
Exactly. When evaluating at a 128K context length, their sparse adaptations reduce the prefill computational cost to just 0.32x compared to standard full attention.
Wow.
And the decode cost, which is usually the hardest part, drops to 0.20x. It is essentially an 80% cost reduction on decoding long sequences.
That is wild. Plus, for handling those ultra-long videos without crashing the memory during inference, they implemented a chunk VIT strategy.
Yes, chunk V.
Instead of trying to load 2 hours of video frames into the vision transformer all at once, the frames are processed sequentially in discrete chunks. Then the resulting embeddings are merged. It drastically slashes the peak memory requirements.
It's the difference between a model that looks great in a theoretical research paper and a model that you can actually deploy in a real-world edge environment.
Speaking of real-world deployment, let's look at the benchmarks. Because this 3B active model is competing against closed-source behemoths like Gemini 3.5 Flash and Qwen 3.5.
And holding its own. Its performance on the TimeLens benchmarks is particularly notable.
TimeLens measures fine-grained temporal grounding, right?
Yeah, meaning the model's ability to pinpoint exact moments across complex datasets like ActivityNet or charades. KaiVL 2.0 establishes absolute state-of-the-art records there.
That's impressive.
It isn't just summarizing video, it's identifying split-second actions better than models with significantly higher active parameter counts.
And on Video MME V2 and LongVideoBench, it shows massive nonlinear scaling. It's synthesizing deep evidentiary chains over hours of footage. But honestly, my favorite part is that the coding metrics didn't drop.
Right, avoiding the catastrophic forgetting.
Yes, it puts up incredibly strong scores on SWE-Bench Verified and LiveCodeBench V6. It kept its software engineering chops while mastering hour-long videos.
The quantitative data is strong, But the qualitative case studies in the appendix are where the agentic capabilities really become visible to you.
Oh, the Quanzu multi-domain service agent sequence. I have to read this because it perfectly illustrates what MOPD achieves.
It's a great example.
A user asks the model to arrange a day for their parents visiting Quanzu. Listen to this chain of logic. First, the model retrieves the user's home address and historical preferences autonomously to book a nearby home inn.
Viewlessly.
Next, the user casually asks for a spot-removing skincare serum to be delivered within an hour. The model cross-references local store APIs, calculates the delivery distance from the UEN skincare store, noting it is exactly 412 meters away with a 28-minute delivery time, and then executes the order.
And what's critical there is the error recovery.
Oh, right.
During the hotel booking step, the model encounters an unexpected payment tool error. But instead of failing out of the prompt and giving up, it recognizes the mismatch, corrects the input, and completes the transaction autonomously.
Exactly. And it finishes the whole sequence by searching local in-store restaurant options, finding a Min and Flavor restaurant, and ordering a traditional family banquet set containing ginger duck.
Just a casual ginger duck order.
Right. It manages state tracking across travel APIs, local delivery logic, and visual UI interactions in one fluid sweep.
That entire sequence is the MOPD distillation in action. The model is seamlessly shifting between the tool use expert, the OCR expert, the spatial reasoning expert, and the language expert.
And it's orchestrating all of that while only activating 3 billion parameters at any given time.
Which is just wild to think about.
It is genuinely a paradigm shift for efficiency. KaiVL-2.0 has successfully decoupled extreme multimodal context from extreme computational cost. By rigorously optimizing the KV cache with sparse attention and preventing domain clashing with the top K overlap framework, they've proven that you don't need to activate 100 billion parameters to maintain state over a 2-hour video.
The barriers to entry for long context multimodal agents just dropped significantly for everyone.
It really leaves you wondering about the next logical leap. We've seen that 13 specialized teachers can successfully guide a 3B active student model to repository-level software engineering and complex video tracking without clashing. But, those 13 teachers were still manually maintained and curated by the researchers.
Right, they had to build them.
So what happens when we automate the creation of the teachers themselves? If a future foundation model can dynamically spawn its own highly specialized reward models on the fly, creating a temporary hyper-niche teacher just to solve a specific subroutine, and then seamlessly absorbing that knowledge back into its core using MOPD.
We might be looking at the beginning of fully self-improving agentic loops.
Exactly. And beyond just the training loops, think about the implication for the future of edge AI. If a 3B active model can now accurately track a 2-hour video and execute repository-level software engineering tasks without blowing up the KV cache, how close are we to running real-time, ultra-long context multimodal agents entirely locally on our phones or AR glasses?
It's closer than we thought. It's a wild implication for the architecture you all might be designing tomorrow.
It really is something to mull over as you build your next pipeline. Thanks for tuning into AI Paper Slop, and we'll see you next time.